Thank you, Deidre. Good morning. Thank you very much to the LISA organizing committee for inviting me to give a plenary talk. Thank you, all of you, for coming at this ungodly hour in the morning after your working group meetings at pubs yesterday night. And I feel greatly honored that I was asked to represent my community, a small cross-section of which I am showing you here. Some of these people are here in the audience. All of them were fundamental in developing this fundamental physics community over the past 40, 50 years. In addition to that cross-section, there's also a large group of young grad students and postdocs are working on this area. Can't help but show you a collage of my research group, a group of very smart and funny researchers making fun of how much I like to wear vests. I am not wearing a vest right now, the internet. Anyway, so my talk is going to be about fundamental physics with LISA. And so I put fundamental physics here in quotation marks because what fundamental physics means really depends on who you're talking to. So to a nuclear physicist, for example, fundamental physics might have to do with the state of matter at very high densities, very high pressures, maybe inside of a neutron star as controlled by QCD. To a particle physicist, it might be, for example, the true particle or field nature of dark matter. But to a gravitational physicist, most probably fundamental physics means, or at least to a group of us, the true nature of gravity in extreme gravitational environments, and that's what I am talking about here. So how can we learn about gravity with LISA? Now, what are we going to probe? What questions are we going to answer about gravity with LISA? There's a plethora of them that I'm going to describe in a second. But before doing so, you might want to wonder why, right? So we've tested Einstein's theory to death in the solar system, but there are other regimes where we have not really probed gravity that well. An example of a place where we've probed it very well is here around Earth. So here's a cartoon of Earth and satellites of this system reminiscent of LAGIOS or Gravity Probe B, probing the weak field. Why do we call this a weak field? So the characteristic mass of the problem here is controlled by the mass of the Earth, the characteristic distance controlled by the radius of the Earth, so the characteristic gravitational potential is much, much less than 1, okay? Let's consider now a binary neutron star system reminiscent of what we probe with LIGO and Virgo. So you have two neutron stars, the characteristic mass is the sum of the neutron star masses, the characteristic distance is the sum of the radii of the neutron stars plus the orbital separation. So in the early in-spiral, this is dominated by the orbital separation. So the characteristic gravitational potential, so the ratio of the mass to the orbital separation, in the early in-spiral ranges from, say, 1 part in 100 all the way to 1 part in 10 until merger. When they touch, it's order 1. Okay, so this is neutron stars. We're in a LISA symposium. Replace the neutron stars, black holes is, the same argument holds. So the idea is that we're probing this regime that has not been so well explored before. To understand that, let me plot the gravitational potential here on the x-axis. And on the y-axis, I'm going to plot a measure of the characteristic curvature of the system, because curvature is a representation of the gravitational force. And so the curvature here is the ratio of the characteristic mass to the cube of the characteristic distance. I'm choosing to plot this in kilometers, inverse kilometers. So on the lower left side of this plot is where we have the weak field tests. So things like tests with the LEGIO satellites or with lunar laser ranging. As we go to higher curvatures, we can use double binary pulsar as a probe of more strong gravitational sources. And then we go to the top right part of this panel. This is where we get to these extreme gravitational environments where we can use gravitational wave data to inform us about gravity. So unlike these other observations where I plot them as little points, here I'm plotting them as a set of points because during the observation of the first 2 LIGO events, then we were able to see a range of curvatures and a range of potentials. So from that point of view, it's a dynamical test of general relativity. And it's a test of general relativity in this high potential, high curvature region. So with LISA, we should be able to cover this entire top right side of the diagram. So what are we going to answer using gravitational waves? There are many, many questions, as I said earlier. Here's a cross-section of them that were recently summarized in a Living Review article written by the Fundamental Physics Working Group last year, I think it appeared. So I was formerly a co-chair of this working group with Thomas Hertog and Philippe Jetzer. I think Philippe is somewhere in the audience. He is still a co-chair. So if you're interested in fundamental physics, you can reach out to him or to Enrico Barause or Richard Brito, who are currently in the co-chairs of the Fundamental Physics Working Group. So I can't possibly talk about all of these topics. That would take more than 25 minutes, and Deirdre told me, keep it short. So instead, I'm going to tell you 3 things. And so let's start with thing 1. So the first thing I want to tell you is that Lisa will dig deep into probes of non-GR effects, in fact, to unprecedented levels. So in order to understand that, let me tell you how we probe non-GR effects and how well we're going to be able to do so relative to, for example, LIGO. So in order to understand how, we need to understand the anatomy of the coalescence, which I think Martin's going to tell us more about, I hope, after me. But very briefly, anticipating his talk, a binary coalescence can be sort of separated into 3 stages. There's the in-spiral stage, where compact objects are moving slowly around each other, some fraction of the speed of light, in spiraling and emitting gravitational waves. As the orbit decays due to gravitational wave emission, the objects eventually merge, producing a burst of gravitational waves and forming some sort of remnant object that is perturbed from its final stationary configuration. It has to relax through the emission of ring-down gravitational waves. So here is a numerical relativity simulation produced by the SXX collaboration. You see the in-spiral regime. Here we can, in fact, treat this stage of coalescence using perturbative techniques like the post-Newtonian approximation, expansion in weak fields, small velocities. Eventually, the objects get sufficiently close to each other that you cannot use perturbative techniques. So you have to solve the problem, the field equations, in full numerical relativity, in some sort of 3+1 decomposition. And eventually, the objects merge and relax. The post-merger object relaxes to its final stationary configuration. And you can model that, again, through numerical relativity simulations or through black hole perturbation theory, where you do a perturbative expansion of deformations away from the stationary object. So those are the techniques that we use. Now imagine that you have this like late-in spiral of a binary system, and so I'm going to show you here is the frequency evolution as a function of time, the orbital separation as a function of time, the orbital velocity as a function of time, and you see here the gravitational waves, and here a representation of the orbital motion. All of this is done in GR, and this particular simulation was done for a low-mass system, but for a binary black hole system, it would be very similar since everything scales with the total mass. It doesn't really matter. So I'm going to show you now is the evolution not in GR. Okay, in a particular theory of gravity, it doesn't matter which one. And I'm also going to play the sound that those waves make so that you can hear them simultaneously. Maybe. We'll see if it works. Okay, so they're misaligned. So there's dephasing here because we've aligned the waveforms at the beginning of the in-spiral when they enter the sensitivity band. So you see the sound, it's similar to what you expect from general relativity because there's still chirping, but the chirping occurs at a different rate. And this is precisely what we're trying to measure. But the way we do this type of measurements in data analysis is through the log of the likelihood, right? So I'm plotting here. I'm going to let it play so you can hear it. So I'm plotting here the difference between the non-GR waveform in the time domain and the GR waveform in the time domain. So this is sort of like the integrand of the log likelihood. And what you see is because there is a dephasing, because the frequencies don't match between those two signals, you hear bits. And what you're trying to really do in data analysis is minimize those bits if you're trying to find the maximum likelihood point. I mean, of course, we have to explore the entire likelihood surface, but it is this bit structure that would signal a deviation from GR, as well as mismodeling of the waveform if you have the wrong parameters, for example, even within a GR model. So this is how non-GR effects encode into our signals. So how well are we going to be able to place constraints on modified gravity? So a few years ago, a former student of mine, Scott Perkins, and Emanuele Berti and I explored this question in some amount of detail and came up with projected future constraints for some sources. You see here a plot from that paper. You see the best sources that can place constraints, the best constraint, the current constraint, and the so-called PN order, which the modification enters for what we would call model-agnostic tests of general relativity in the inspiral, or post-Newtonian test, or parameterized post-Einsteinian tests. What I want to point out is that for a large class of these modifications, it is multi-band events that place the best constraints by many orders of magnitude. And so multi-band events, these are about 100 solar mass binary black hole systems that are very widely separated in the LISA band, so like about 10 to the minus 2, 10 to the minus 1 hertz, and that then merge in the LIGO band, and they were discussed yesterday as well. And so you can map those constraints to constraints on particular modifications of gravity. So here's one of them, so-called scalar Gauss-Bonnet gravity, which will probably be discussed more later today at 4 p.m., or also on Thursday at 2 p.m. by Andrea. And so what you see here is the constraint that we should be able to place on this coupling constant of this theory as a function of ear for different configuration of detectors. So don't worry about that. There's like a lot of different symbols here representing different ground-based configurations. What I want you to notice is the current LIGO constraints over here. Here's the projected LISA constraints. Here are the multi-band black hole binary constraints. So this is about an order of magnitude or 2 orders of magnitude better we can do with LIGO today. And multi-band happen to be best for these kinds of modifications. You can also prove many other types of effects, like a variability in Newton's gravitational constant. Again, in this case, multi-band events are better than the massive black hole binaries. But whether massive black hole binaries are better or worse than multi-band really depends on the kind of modification, the kind of non-GR effect that you're considering. So if you look at a mass of the graviton, so you can consider the possibility that the graviton has a mass. If it has a mass, then the dispersion relation of gravitational waves is not as what you would expect, because d omega decay is not 1. It would have modifications. So as the wave propagates from the source to us, these modifications accumulate, and they grow with distance. Now, the systems we can see farthest away are massive black holes, supermassive black holes. So the more massive the binary black hole system, the better the constraint we're going to be able to place. And you see that here, allowing constraints that many orders of magnitude better than what we can do today. So that's like a little sample of what we can do. There's a lot more in the review paper and in those references I added. So let me tell you the second thing I wanted to tell you, which is that we're also going to be able to prove new physics. Maybe this is the most interesting part. And there's like lots of different kinds of new physics that you could probe. I'm just going to talk about 2 examples. One of them is gravitational parity violation, and the other one is polarization of gravitational waves. So for the experts, gravitational parity violation can also be probed with ground-based instruments. But because LISA can see so much farther away than advanced LIGO today, we can probe parity violation through a much larger regime of the cosmos. OK, so why parity violation? Well, we know that parity is broken by weak interactions in particle physics. We know this from observations of the decay of cobalt-60, from observations of pion decay. So the question is this also broken gravitationally? So what would that look like? Let's imagine we have our little supermassive black holes here, and here's us, and here are the gravitational waves. Okay? So this is almost as realistic as the previous talk. And so generally, you would have a linear combination of the polarizations of gravitational waves. So let's say that there's only plus-cross polarizations or left-to-right polarizations. Now, if parity is broken gravitationally, then the left and the right polarized gravitational waves would satisfy different propagation equations. So here's an example. The dots mean time derivatives. H is the Hubble parameter. And you see here there's a plus minus. So one of the modes would carry a minus, the other one would carry a plus, so they satisfy different propagation equations. The solution to this is an amplification or suppression of the amplitude of the gravitational wave that scales with distance traveled. This is why I was saying that LISA would be so good at probing this effect. So that's our amplification and suppression. And then you can ask, like I was asked many years ago, whether you can actually distinguish this effect from other parameters that enter into the waveform, like post-Newtonian corrections or the inclination angle, things like that. And it is true that there are degeneracies, but people like Max Easy and Will Farr, and Macarena Lagos, and many others have shown that those degeneracies can be partially broken, and so we can, in principle, probe this effect with black hole binaries. And roughly speaking, we should be able to probe this effect to as far as we can see gravitational waves. If we see gravitational waves from sources at redshift 10, optimistically, then. Okay, what about polarizations? All right, so for those of you that have taken GR recently, then this will be old news, but for many of us, this is a refresher. Gravitational waves come in two polarizations. This is the plus mode, and the cross mode would be rotated by 45 degrees. So usually we see this in like a static figure of point particles and like with little arrows, and then the wave here is coming out of the screen. And so this is a little movie that was created by my student Kristen Schumacher and undergrad Srivastava and many others who are working in a virtual reality education outreach type project. And what's nice about this simulation is that you can place the observer anywhere you want. They call it teleporting in VR. And so here's a view that's sideways for this sequence of rings. And here's a view that's 45 degrees. So this is all very nice for the plus and cross polarizations. But if you're in a modified theory of gravity, you can have up to 6 polarizations of gravitational waves. You have 2 tensor polarizations, the plus and the cross. You can have 2 scalar polarizations, which we call the breathing mode and the longitudinal mode. And you're going to have 2 vector polarizations, which we sometimes call the X and the Y polarizations. And that's a little bit hard to see. Like, I never fully understood this when I was a student and just seeing the static pictures of what exactly was happening with the plus and the cross. So if you actually look at this 45 degrees, it becomes a lot clearer. So the gravitational wave is going through here. Here's the breathing mode. It's sort of like breathing in and breathing out these circular particles. And here's the longitudinal mode. It's pushing the rings in and out. Okay? That's cool. That's cool, right, Idra? Yes, okay. And here are the vector modes, okay? So the vector mode is like saying no and yes. And it's pretty cool. I mean, in reality, any modified theory of gravity that you consider out there, the most generic one will have all 6 polarizations. So you're not going to see just one of these. You will see this, all of them together. Okay? Okay. In reality, we know that the plus and the cross should be much larger than any other additional, or we expect, just because if there's these additional polarizations, there would be more energy loss in binary systems, and we observe a certain amount of energy loss in binary systems. But still, modifications of this type is what we are searching for. In principle, you can also imagine that there could be just scalar or just vector modes that arrive at detectors, because in principle, in modified theories of gravity, the polarizations can travel at different speeds than the speed of light. The plus and the cross have to travel at the speed of light as measured by LIGO through the coincident GW170817 event. But the other polarizations were not constrained by that event. So they could travel faster than light and still preserve causality because they have their own independent null cones. And so if that's the case, if there's a scalar mode that travels faster than light, then that mode would arrive at the detector earlier. And so we would perceive it as just a scalar mode. And then the tensor mode would arrive later. And so that's a theoretical justification for just looking at scalar or vector modes. So how do we do this? We do this by looking at null channels, in principle, or by looking at parameterizations, like the PPE parameterization of waveforms that deviate from general relativity and include additional polarization effects. where you just do a Bayesian MCMC or nested sampling run to estimate the parameters associated with the amplitude of the additional polarizations. Didra says I'm running out of time, so very quickly. Thing 3 is that we can probe gravity or non-GR effect with new sources or with different parts of the wave that we cannot really use that well so far. So I want to concentrate on 2 of these. One are MRIS, which will be discussed a lot more on Thursday. Another one is ring down. Okay, so regarding ring down, after merging at sufficiently late times, the ring down gravitational waves are well described, as you know, by a sum of quasi-normal modes. And the frequencies of those modes depend in GR only on the properties of the final black hole object, so the mass and the spin of that object. In modified theories of gravity, you can have additional parameters because there could be a scalar field or a vector field that's anchored on the black hole, and so the frequencies would depend on more than the mass and the spin. Therefore, it's important to understand what the quasi-normal mode frequencies are in different theories of gravity. This was very difficult because up until recently, there was no way to decouple the perturbed field equations in modified theories of gravity, but now there's 2 approaches. One is this modified Tucholsky approach, and the other one is the metrics approach. The Tucholsky approach deals with separation of the Newman-Penrose equations in theories that are deformations from GR, whereas the metrics approach leads with metric perturbations, and so deals with the coupling of the differential equations through a spectral decomposition. And I think Adrian Chung will discuss this again later today at 4 p.m. in the modified gravity section. But here's an example of how well this metric approach works. These points are the quasi-normal mode frequencies in GR of curved black holes. You see they lie on top of this great line, which is not a fit, is the known Tucholsky result of GR. So the points are obtained through a completely different method. You see they agree very, very well for black holes of different spin, so that's 0.95, this is 0. And it can also be applied to other theories of gravity, allowing you for the first time to calculate the quasi-normal mode frequencies very accurately in theories outside of general relativity for black holes that are not rotating slowly necessarily. Okay? And so with these, we can now build parameterizations of what the quasi-normal mode frequencies are, and in a more theory-driven approach, test GR and probe gravity with ring down. And also, of course, you can probe GR with extreme mass ratio in spirals. Andrea Maselli will talk about this on Thursday, I think. But in general, there's 2 philosophies. One is that what we want to probe are the properties of the supermassive black hole here. Maybe those are not curved black holes. Maybe they are something else, and so the gravitational field outside of that black hole deviates from that of Kerr, and you can consider adding or measuring the multiple structure of the gravitational field produced by the supermassive black hole as probed by the little small object that's zooming in and out. More recently, people have been testing other symmetries of the Kerr solution, like equatorial symmetry breaking, suggested, for example, by fast-spall solutions, or testing the ability of the black hole to absorb gravitational waves, which has been suggested by exotic compact objects that predict some amount of reflection. Another way of probing gravity is to consider the structure of the small compact object, the so-called scalar hair. So Thomas Sotirio, Andrea Maselli, many others have argued that in a very large class of theories, there are the small object in this binary system would have a scalar field anchored on it that is much stronger than the scalar field that would be in the larger black hole, because the scalar field would scale with curvature. Curvature is much stronger for the smaller object than for the larger object. So as the small object zooms and moves around, the scalar field that's tied to that small object would move around with it. And in doing so, that scalar field will emit scalar waves, which would actually force the binary to shrink faster than in general relativity. And that is something you can probe, you can test. And here is a recent result by Lorenzo Spieri and Susanna Barsanti and Andrea and many others who did a Bayesian analysis to predict how well we would be able to measure the properties of this scalar hair. And you see here different posterior probability distributions, constraints on the so-called scalar field charge or monopole charge of this small compact object. So I'm going to end now before Deirdre kicks me out, and I hope I've convinced you that With LISA, we can probe gravity in a new way, with new sources, and in a deeper way that we have been able to do so far. So everything is very cheerful and fantastic, but I think a lot more work still needs to be done. There's a lot of, we're searching, in principle, for very small deviations from general relativity, or we're trying to constrain potentially very small deviations from general relativity. And when doing so, one has to be super careful about systematics that might appear in our modeling. The systematics can be in the way we model the noise. It could be in the way we model the data. It could be in the way we model the waveform itself, or the modification to general relativity. We don't want to be in a situation where we think we've detected a GR deviation, and in reality, there was just some noise artifact that we didn't account for, or there was an issue with the gravitational wave model in GR that we did not account for. So people are very actively working on this issue of systematics so that we can make our probes of non-GR effect robust. So this is very important, but I am optimistic because this large group of people are making great progress, and I think that they'll be able to do it. So thank you.
Nico? All right, we do have time for some questions. There's one over here. Do you see that?
Hi, thanks, Nico, for the very good talk. Right here. Can you see me? Hi. Yeah. So thanks for a great talk. I just had a question about the last point that you mentioned. So you mentioned something about trying to deal with this sort of coupling with all these other effects which are consistent with GR, but otherwise not a vacuum memory. In my understanding, any modification due to GR would be like a small secular perturbative effect. And what that means is that it won't have a very signatory perturbation to the vacuum trajectories in an MD model, for example. So I understand there's like a fundamental limitation on how you can model these effects, and that they would remain correlations with all these other effects, which will also show up as these perturbative secular effects. So can you like highlight how some of these projects are trying to deal with this decoupling and looking for specific signatures for modifications of GR? Thank you.
Yeah, so let's see if, I think I had a slide precisely about this. So here's my wish list or warning list of things you should do. It's not like I'm pandering to my Irish friends, but whatever. And so there's many things that you can do to make sure that your effect is real and it's not just fake. So you can calculate base factors when you're doing model selection for your GR and non-GR effect. That has to be fair with your non-GR effect. The fitting factor also has to be calculated to make sure that the model is capturing the signal well and you're not leaving behind any additional SNR. But even then, you can be confused. So you have to make sure that this whatever effect that you are measuring is consistent across the catalog of events, and it's not just a fluke because of a particular event that had like additional precession or something like that. But another way that people are dealing with this decoupling of degeneracies between, say, GR effects or astrophysical effects and modified gravity is to model those effects and then marginalize over them. Okay, so if you know that your waveform model has calibration parameters that are not exactly calculated, but they have been fitted within some error, you can allow those parameters, those calibration parameters, to not be fixed at the maximum fit value, but to actually be parameters in your model where the prior is given by the calibration posterior. So you enhance the dimensionality of your model, and then you marginalize over them during your MCMC search. So these are like the same with glitches, right? Like instead of just assuming that they're not there, you could, or you could model them, or gaps, you could model them and then marginalize over them. So.
Was there another question over here? I thought I saw a hand. No? So if you see Nico and I do this, it's just there's really bright lights. It's like being on the stage.
It's really bright.
Nico, I think this probably isn't unanswered.
I think Sean has a question.
Someone has a question? Who? Sean? Sorry, Aaron.
But you can also ask me a question if you want. Doesn't matter.
Ask you later.
So you talked about worrying about how degenerate these effects are with regular GR. How degenerate are they with each other? Like, I'm wondering, can you, in reality, you observe something, how likely do you think you'd be able to say, like, aha, this is this particular modification, this is what's going on, versus, like, right, because it seems like the space is kind of infinite.
Yeah, it's not quite infinite. So there's of course things we might not have thought about, so from that point of view, it's infinite. But based on the effect that we have considered, like if you're looking at an accretion disk effect back in like 1 million years ago, when we were postdocs, we looked at this, and it looks like due to migration and so on, embryos would potentially be affected by accretion disk effects that would mimic a negative post-Newtonian order effect. And I think this was recently confirmed by Lorenzo, Spieri, and others, where they did a much more careful analysis and so on. So we know, for example, that those accretion disk effects typically excite negative PN order effects. A glitch, on the other hand, is like at a very abrupt change in your data. And so that tends to excite higher post-Newtonian order effects, like a 4PN or a 5PN effect. And there's like a partial, you can sort of partially break those degeneracies that way. Plus, there are some sources where you might expect astrophysical effects, whereas in others you wouldn't necessarily. So,
Thank you.
All right. Let's thank Nico again for his fun talk. Sorry. Catch up.